The last topic of this lecture is LU factorization or LU decomposition. In many engineering applications, when we solve AX equals B, the matrix A remains unchanged while the right-hand side vector B keeps changing. If we do Gauss elimination, the B vector and always tag along because we concatenate them together. You have to calculate it in every operation. But LU decomposition focuses on factorization of the coefficient matrix A only. In LU factorization, the decomposed matrices are used to efficiently evaluate different right-hand side vectors, and we're going to talk about this in later slides. LU factorization methods separate the time-consuming elimination of the matrix A from the manipulations of the right-hand side B. Therefore, once A has been factorized or decomposed, multiple right-hand side vectors can be evaluated in an efficient manner. However, we still use the equation set here as the vehicle to prove that A equals L times U, where L is the left triangular matrix. However, we still use the equation set as the vehicle to prove that A equals L times U. First, rearrange the equation set AX equals B to be AX minus B equals 0. After we do Gauss elimination, we get the new equation set to be U times X equals D, where U is the upper triangular matrix format of A and D is the updated B. Assume there is a lower diagonal matrix L that can be left multiplied to U times X minus D equals 0. Then we have L times UX minus D equals AX minus B, because both sides equals 0. By the association rule that we introduced in the first part of this lecture, we get L times U equals A and L times D equals B. To solve for X using LU decomposition, first, the parameter matrix A is decomposed to U and L. Then, we use forward substitution to get D by L times D equals B. And then we use backward substitute to get X. To solve for X using LU decomposition in the equation set system, first, the parameter matrix A is decomposed to U and L. Then we use forward substitution to get D by L times D equals B. In the end, we use backward substitution to get X by U times X equals D. The factors employed to obtain the U can be assembled to get L, proved in the following example. This is an example of solving an equation set using LU decomposition. The system to be solved is here, and X is the unknown. The first step is to solve U, which is the upper triangular matrix, by forward elimination, which is the first step of Gauss elimination, but without considering B. And then we solve L, which is the lower triangular matrix, and by calculating F21, F31, and F32. And then we put these into the specific position in the L matrix. Calculating back, we get L times U equals to the parameter matrix A, as can be seen here. The following is the LU decomposition to solve the equation set in Matlab. The built-in function LU is to calculate the lower and upper triangular matrices L and U. There is a simple demonstration of solving the three-equation set problem using LU decomposition. The built-in function LU will be called. The middle step value d can be calculated by L left divided by b, and x can be calculated by u left divided by d. Remember how we calculate u by forward elimination and L by element-wise calculation. If the A matrix is symmetric, special solution techniques are available, such as Cholesky factorization. If A is symmetric, A can be decomposed as U transpose times U. That is, L equals U transpose. So the terms are multiplied out and the items are calculated in the following way for UIIs and UIJs. Here is an example showing the element-wise calculation for U. How to calculate L? Well, it's simply the transpose of U. This is an example of solving an equation set where the parameter matrix A is symmetric. Since A is symmetric, we can call the built-in function CLOL for the LU decomposition of A using Cholesky factorization. This is an example of solving an equation set where the parameter matrix A is symmetric. Since A is symmetric, we can call the built-in function CLOL for the LU decomposition of A because we can use Cholesky factorization. And then, following the regular equation solving steps, forward substitute and backward substitute. Then, in the end, we can solve for x. There is a simple Matlab demonstration of calling the built-in function CLOL for Cholesky factorization for solving the equation set where A is a symmetric matrix. You are expected to do this exercise by hand, which is to determine the LU factorization for the following matrix, and check your results by validating that L times U equals A.